Okay, well, thank you all for coming, and particularly thanks to Lars, because I kind of dropped him in it and said, can you give a talk at the end of the week? And he said yes. So that's the reason we're not at the University of Birmingham, but we're pretending to be. And he's very kindly going to talk about some of the things that were mentioned in the workshop last week particularly, and sort of have been touched on in a little bit in some of the discussions this week, particularly about what happens as the dimension of the number of multivariate observations kind of grows. So without further ado, Lars, who's going to talk about
Okay, so thank you very much for the invitation, and sorry about that it says University of Birmingham. I asked several times whether I need to give a talk here. Nobody responded. Okay, so I asked how to get into the apartment, okay, which was again ignored. So when I arrived, I didn't have an access code. Okay, but I managed. So I will give 3 talks at the University of Birmingham. And surprisingly, okay, John picked the middle one. So I hope that without the introduction, it will make some sense. So this is based on a joint work with Maria Huskova and my student Jia Wang. Okay, so this is the outline. I will talk about, okay, that the change point model in panel data, how we are using essentially when we would like to test if there is a change in the mean, we are using the standard Q-sum technique. Okay, and this one is essentially tailored toward when we are looking at panel data there. I will discuss that essentially the condition in some sense optimal, and I will discuss essentially why this optimality came into the picture. There will be 2 applications, which I would say interesting. Okay, and it shows essentially what happened in some sense in Eastern Europe after the fall of the Berlin Wall. After that, when assuming that there is a change in the data, there will be an estimation of the time of change, the definition of the estimator, after that one, the asymptotic distribution, and again, there will be some applications, but essentially there will be no simulations because those are still going on. Okay, we changed our mind what we would like to see in the simulations. So here is the model, okay, the panel data model there. So what we assume, okay, the observation xit can be decomposed in a way like that one. Mu I, this is the mean, okay, of the ith panel there. If there is a change, the change occurs at the time t0 in every panel there, and the size of the change is delta I. So of course, okay, if in case of one panel delta is 0 there, then in this case there is no change of panel. So essentially this is not assumed that all the panels must change. Some of them may change, the other one may not. Then there is the next term there. This is the gamma I eta it. Eta I is essentially the common factor there. So this means that essentially when you are looking at this model there is a connection between the panels there. The connection is essentially given by this common factor eta t there, and the gamma I, this is the loading of the common factor for the ith panel there. And this epsilon it, these are nothing else but some kind of an error terms there. So what we are looking at here, okay, so n is the number of the panels, t is the number of the observation each panel there. So what we would like to essentially, this is what we are checking, okay, whether the mean will change to mu I plus delta I there, okay, and how this is working out and what we would like to know. So essentially, only thing what is observed xit, we assume that the common factors, okay, those are unobservable variables there, and based on this one, we would like to do some kind of a statistical inference. I am interested essentially in limit theorems there. In our case, both n and t, okay, these are going to infinity there together. In the econometrics literature, there are several results when n goes to infinity first, then t goes to infinity, or t goes to infinity, n goes to infinity there. In our cases, essentially, we will have the both of them are going to infinity there, and both of them will be large there. The goal is what we would like to see, that essentially we would like to cover the case that n, the number of the panels, is larger than t there, and they will be essentially optimality result like, okay, how larger n can be than t there. There is an interesting example in the Journal of Finance there. Okay, so these 2 authors there, they were looking at companies in the United States there. The number of the companies they were considering in the study there was between 200 and 37,000. Okay, so this means that the number of the panel was large. Essentially, when they had all those companies there, then in this case, the number of the observation, which covered essentially that many companies, was only 20 there. The claim is that essentially it's very, very rare to get lots of information about companies there because they are considered confidential there. The other thing is that there are relatively few companies. Okay, oh, I'm pushing the wrong thing. Okay, there are relatively few companies in the United States which will survive for a very, very long time. And typically they are reporting annually or semi-annually there. So this is the only thing what they had there. And they were looking essentially, okay, so whether the volatility was changing, what is the reason this one, and so on. So essentially this is just a motivation for this type of studies there. Okay. Again, so what I said is written down again. The standard assumptions are the following there, okay, that the mean of this error term is 0 there. Again, this is due to the parameterization, it is missing there. So again, the expected value of the common factor is 0 there. It is not. Of course, you can build up this one here into the mean there very, very easily there. The change point problem is defined in the standard way. The observation period is from 1 to t there. If the change is outside of this observation period there, of course, we cannot see it. So this means that for us, there is no change point there. And under the alternative, okay, it happens between 1 and t there. So what is essentially the interesting things about that one here? So if you look at the model there, so we will have the situation there, and I think one of the applications, when the t is like between 35 and 40 there. It is assumed that this is a time series. So imagine like this is a linear process and so on. So if the number of the observation is that small, there is dependence between them. In case of one panel, it is very, very difficult essentially to do any kind of statistical inference. Yeah? But if you have more panels there, like for example, the number of the panels is 30, and the number of the observation is only 30 there, then in this case, essentially, you are looking at 30 times 30 information, which is 900. So this means that essentially the number of the observation for the statistical inference is much, much larger than it would be in case of one single panel only there. So this is the reason why this type of models were suggested, like in the paper what I mentioned earlier. Roughly speaking, the authors are trying to grouping them, for example, being in the same sector. So even they have observations like for capital T 30 there, the number of the panels is like between 30 and 50 there, and in this case they have a large amount of observations. What is the other interesting feature of that one here? Okay, in this case, if you are looking at the panels there, the only common parameter is T naught. So roughly speaking, when you are looking at the time of the change, this is the only parameter which is showing up in all the panels there. And essentially, we are looking at all the other variables like the mean, the change in the mean, and all other things like gamma I and the variance of the error terms and nuisance parameters there. So roughly speaking, we are not really interested per se, at least in this talk, to estimating them. Only thing which is interest for us, the common parameter, and if everything goes well, then in this case, the number of the observation for T naught will be n times T. If you would like to estimate, for example, mu I there, whatever you do, the number of the observations will not be more than T there. Okay? So this is essentially what we are trying to do. Here are a few references. So this one here is essentially an interesting one by Atta Clinton and Xiao there. They are essentially modeling climatic change in the United Kingdom there. We studied these two papers the several papers by Bai, which I'm mentioning here. These are one of the first one about change point from less panel data and so on. And my talk is based essentially these papers there, which were already published. And when I talk about the estimation of the time of change, this is essentially still not not finished that, but hopefully it will be finished by Sunday. Okay, so now let's see, okay, so how to do the test statistics there. Okay, in case of the ith panel, if you are looking at this process here, this is nothing else but essentially the so-called Q-sum, okay, process there. Here this is the partial sum, and this is compared essentially the total sum of the observations in the ith panel there, and then essentially you are using that this is like the X percentage whenever you are comparing this one to the sum of the first X terms there. So this one is essentially the Q-sum process for one panel there, and what we are doing here, we are taking essentially the sum of the squares of the Q-sums normalized, okay, by these terms there. If the observations were independent, then of course, okay, this would be the sample variance. Otherwise, okay, you have to use the long-run variance or something like that one, okay, to do this one. First, I will talk, okay, do the theoretical properties, so I will have this sigma square there, and then later, okay, I will comment like how to replace this one with an estimator, and I would say as standards in asymptotic statistics, it will not make too much difference there. Okay, so here are the conditions there. The first condition is that when you are looking at the error terms between the panels are independent. This is a natural assumption there because essentially the dependence between them, this is measured by the common factor there. Okay, so we essentially would like to see if there is correlation between them, which is causing it. Then it is assumed that if you are looking at the observation in a given panel, that this is a stationary sequence there. Again, natural assumption, if we would very hard, probably, okay, you can get results when stationary is not assumed. And here is the next condition there, which looks, I would say, somewhat strange there. What we are looking at essentially, we are looking at the partial sums of the error terms there, and we are computing the new moment of that one. So you can look at this one here, that this is nothing else but the long-run new moment there. And the assumption is coming up essentially somewhere here there, that when you are looking at, okay, so what is the new moment there, that this one here is in the order what you expect in case of the weakly dependent variables there. Yeah? So if you think about this one here, okay, that if you are looking at the sum of these random variables here, okay, if everything is going well, this is a weakly dependent sequence. In every case, is essentially this is supposed to grow like t to the power nu half. Yeah? Okay. So this one here, I would say, is a very interesting mathematical questions there. Of course, our goal is that we would like to have that the partial sum of these random variables will satisfy the central limit theorem there, okay? Asymptotic statistics, normality will come out, so sooner or later you have to prove it. The question is, okay, what you need to assume that a statement like this one will be true and covers all the interesting cases there. It turns out a conditions like this one, okay, this will give you, this is essentially growing at the rate, whatever, okay, it is assumed there, then in this case, okay, that this will essentially give you the central limit theorem. I have friends who are excellent probabilists, so I ask the following question from them. Let's assume that you have a sums of stationary random variables. You know that they have new moments there. You know that they satisfy the central limit theorem. It turns out it implies immediately that essentially the order of this sum when t goes to infinity must converge exactly to t to the power nu half. Yeah? So instead of saying that we are mixing sequences and things like that one, so what is essentially assumed that you have something about the behavior of the partial sums like that one. The condition about the common factors there, that they will satisfy in some sense the central limit theorem, no mixing, nothing like that one, that essentially they're converging weakly to a Wiener process there. Here there is no variance there because this is already built up in the gamma i's. Okay. So why this condition is a very good one? So there are a few examples when these conditions are satisfied. So if you are looking at the ith panel there, then in this case, of course, everybody can compute the variance, so this is a correct one. And then when you are computing the higher moments there, then in this case you can use Rosenthal's inequality, and you have exactly, okay, what we wanted to have there. The other example, okay, the linear processes there, which are defined in a way like this one. So the coefficients essentially depends on the panel there, and you have these IID observations there. So using the standard Phillips and Solow representation, you can write it down, that's a sum using these coefficients there, and again the Minkowski's inequality and whatever you know for IID random variables again implies that essentially you have exactly a rate like that one. The next one, okay, so this is the martingales. The inequality, what we would like to have, this is in the book of Hall and Heidi. Okay, they already looked at this one when they proved the central limit theorem for the sum square integrable martingales there. If you like, volatility process is there. I mean by volatility that the error term is written in a form like that one, that this one is essentially the volatility part there, epsilon it. These are just a sequence of IID random variables there. Then again, you can show very, very easily that all the cases which are considered in the book by Frank and Zekoyan, 2010 there, then again, this inequality, using again Rosenthal's inequality there, it is satisfied. Okay, so this means that all the processes what we were interested, essentially this condition is easily checked or already people checked there, so there is no problem with this one here. If you are interested in mixing, then of course the situation is a little bit more different there. So first of all, okay, there are lots of different mixings there. If you read the book of Duhan, there is mixing starting with alpha going to omega there, okay? So essentially saying mixing is not so much there. There is a book by Bradley, and this is 3 volumes long, altogether very, very close to 1,200 pages there. And this is full of this type of inequalities like that one. So don't forget in probability theory, in classical probability theory, how to prove this type of inequalities. This was essentially part of research, okay, how to do this type of things. So we assume that we know it, okay? So people already did the hard work for us. Okay, so look at this one here. So let's go back, okay? This was the process what we defined. And the question is, okay, how this is behaving, this one under the null hypothesis there. The first what is assumed, sorry, okay, so part is missing there, I will say because John edited it, he edited out that n divided by t squared, it goes to 0, yeah? And then the next term here is then the average when you are looking at the sum of the squares of the loading divided by square root of n, it goes to 0 there. So this means that essentially the correlation between the panels is small, yeah? So those are not very strongly correlated. In this case, you have a limit results there. The limit is of course normal, as I said, this was the goal, some kind of a normality there. The mean is 0, and this is, okay, what you are looking at is the covariance function there. The covariance function, okay, doesn't look, I would say, very, very complicated one, yeah? Okay, and of course all my students would be very, very happy about that one because they say, oh, this can be simulated very, very easily there. Okay, but we are very nice supervisors, so we showed them the following, that if you work a little bit hard, then you can compute and you can show how this one is related, okay, to a Brownian motion there. So there is a time transformation inside, and there is another function inside there, yeah? So this means that if you have some kind of a good program which will generate for you Brownian motions, okay, or Wiener processes there, then in this case essentially is a piece of cake generate this process there, okay? This one here is essentially a very, very strange looking one, okay? It turned out we were not the first one, okay, who discovered this one. It comes out in the econometric literature like the iterated Brownian bridge there. The reason is, this is the representation for a Brownian bridge, and this is like some kind of a squared version of that one, so this is squared and the argument is squared. To see the relation, this one here to the Brownian bridge, it's coming from this, this argument here. So everybody knows, whoever worked with Q-sum processes there, that for every I, when t goes to infinity, this is converging, okay, to a Brownian bridge there. So essentially, what you have to do is compute the limit, the sum of the squares, okay, of independent Brownian bridges minus the mean there, and in this case, okay, you will get this process there. So roughly speaking, okay, here in the covariance, you are looking at the covariance of the squared Brownian bridge there. Okay. So this is just the testing procedure, okay, if the maximum is large, then in this case we will reject. So questions, whether this condition that n divided by t squared goes to 0 is optimal. Don't forget, okay, people in finance, they wanted to work with this one here when n is 37,000 and t is 20, yeah? Okay, my comment is that essentially it will not work. What we proved is the following, okay, that the common factor is negligible. We showed that there is essentially a non-zero bias term here. So essentially, if square root of n divided by t naught goes to 0, then in this case, okay, v and t bar, this is exactly the order of that one. So this means that if square root of n divided by t goes to a constant, there is a non-zero bias. If this one goes to infinity, then in this case, essentially, this process will go to infinity there. So the warning is, if the number of the panels is very large and the observation period is small, then in this case, you will reject. Yeah, whatever is happening there.
Is the reason for this because you have this mean, each one has its own individual mean, and basically you're aggregating all those errors?
Yes, essentially the errors what you are aggregating is the bias which is aggregated there. So don't forget, essentially you have the number of the panels there is n, the normalization is square root of n. So this means that there is some kind of, let's assume the same bias in every panel there, then in this case the bias will be square root of n times the common bias there, yeah? And in this case it will kill everything there. So in this case, how to deal with the bias is a very, very important one. The next one here, okay, the condition about this one here is essentially like how much correlation you can allow between the panels there. If this one goes to infinity there, again, then the process is going to infinity. So if you are looking at very, very strongly correlated panels, again, you will reject there. Now, what is the reason of this one? The reason is very simple. Essentially, these gamma i's are very, very big. That roughly speaking, instead of looking at n panels there, you are looking at one single one, because all of them are essentially the same. They are completely determined by the common factor there. Okay. So again, these are under the alternative. So this means that there is a change there in the middle. Okay, and this is essentially assumption about the sizes of the changes there. So this means that they do not have to be very, very big. Yeah. Because you are taking the square, you sum them up, you multiply with t, that only divide with square root of t. So this means that even very, very small changes, okay, so will be detected there, and you can assume that even those are random variables there. As I pointed out, okay, you have to estimate the variance there. Okay, no independence is assumed, so we are suggesting the long run variance there. Okay, how to do this one, the kernel estimator there. If you look at this one here, okay, that it is assumed that the kernel has lots of derivatives, okay, in the neighborhood of 0 there. Why? Because this reduces the bias. So if you think about, okay, this flat top kernel, which is used by several people there, of course, you will have this property there because it is constant in the neighborhood of 0. So this means that essentially there is no bias which will propagate there. Okay, so you can do this one, this replacement there, and the limit is still the same. Okay, now, okay, this is the application part there. So one of them is, okay, the famous Gini index, okay, looking at inequalities there. Okay, so this one here, you are looking at 159 countries there. And since essentially lots of them is missing here and there, okay, so we looked at 33 countries, and this is going, okay, I don't know, okay, so how many years there? I think, okay, this is like 20 years there. Yeah. So the question is essentially, okay, whether the index is changing or not. So whether there was like some kind of an improvement about inequalities and so on. Okay, so this one here is the Northern European countries there. okay, this one here is Norway, okay? So Norway is essentially constant, and all the, I would say, okay, the Northern European countries there, okay? So even in some cases, okay, so this is going down there. Yeah, so less inequality. This is the other interesting one. So these are the former socialist countries there, yeah? So if you look at this one here before the fall of the Berlin Wall, essentially there are not too many, okay, very rich and very, very poor people there, yeah? After, okay, the wall came down, and this became, I would say, okay, so a completely different one. So if you are doing the testing there, then in this case turns out that there is no change in the Gini index, okay, this is rejected there, very, very high significance level there. If you separate the countries there, in case of, okay, so these, I would say the Western countries, the Gini index is constant. If you put together, okay, so Eastern Europe with like Latin America and so on, then in this case the Gini index is changing there. If you are looking at the pictures, okay, that it turns out that the difference between the poor and the rich, okay, this essentially increased. The other interesting one is the corruption index there. Again, this is essentially very nicely collected by the United Nations. So if you are down here, then in this case, okay, then you have corruption. So 0, this is essentially the absolute corruptions there, and Angola is getting very, very close to that one, yeah? If you are looking at this one here is, for example, okay, Sweden there, 10 is the maximum what you can get. So roughly speaking, essentially, it's very nice and very stable. There is no corruption, okay, in Sweden there. Okay, so, yeah, oops. Again, if you do, okay, so, yeah, I always try to put essentially countries there when hopefully there is no one from the audience. Okay, maybe the Swedes, okay, they would like it that they are not corrupt. Again, essentially the assumption that the corruption index is stable, this is rejected with a very, very high significance level there. The most interesting one, okay, so I'm looking if somebody is really from China. The interesting one is China. China is going up and down there. Why? Because essentially they have campaigns against corruption, okay, and the height of the campaign is somebody executed. After that one, the corruption index drops, and then it's very nicely come back a few years later. Okay, so the second part of the talk is, okay, and this is about the estimation of the time of change. So let's assume that we rejected the null hypothesis, that there is no change in the mean there, and now we would like to estimate essentially the time of change there. This one here is like, okay, this is the sum of the squares of the Q sums. The only difference here, okay, that the sigma square is gone. Why? Because essentially the estimation of the sigma square is very, very difficult, okay? So when you know that there was a change there somewhere in the middle, and you are trying to use a kernel estimator based on 40, 50 observations there, okay? This is very, very highly unreliable, so therefore sigma square is not in the definition there, so it will come back later on in other type of constants there. This is the standard assumption here, okay, that the change is happening somewhere in the middle of the data there. If you look at this one here, then, and again, this is the standard cheating in this field, we are saying that the parameter is T0. Yeah, this is the time of the change, but essentially the real parameter is theta, okay? Like in what percentage of the data the change occurs there. Okay, so when we will have the results, okay, so what kind of quantities we have there? This one here, okay, the sum of the squares of the changes there, okay? Of course, it is important, certainly if the changes are larger, then in this case, essentially, we should be more accurate to find the time of change. The other one, again, like the sum of the gamma squares, the gammas of the loadings. Again, we said if the loadings are very large, then in this case, okay, much harder to see what is happening there. So this will be again one term which will be important. And the other one is the interesting one here, okay, that essentially the product between the size of the change and also this essentially this factor there, yeah? So essentially like if they are changing signs or something like that, that roughly speaking, okay, this term even can go away. A few assumptions there again, you need some kind of an assumption there, okay, that this one can be very, very small. It is measured by that one. And again, the next one here, that this cannot be very, very big there, okay? So otherwise, you cannot even detect the change there. Okay. So first one, the standard assumption means that we have all this assumption, okay, at the beginning, like the panels are independent, only the common factors, okay, so connect them and so on. The first result is an interesting, okay, the delta nt goes to infinity there. What is delta nt? This is the sum of the squares of the changes in the panels there, yeah? So this is supposed to be large there. It doesn't mean that each of the changes must be large because you are taking the sum of them, yeah? So they can be small, but only the sum must be do. Okay, and this assumption means that essentially when you are looking at, okay, so it's essentially like the correlation between the panels, okay, this cannot be too big. In this case, it turns out, okay, that the estimator for the time of change is exactly this point there. So it's essentially if the change is very large, then your estimator will hit, okay, this T naught with probability 1. Next one here, further notation for that one, okay? So what is this one here is essentially you are looking at, this was the sum of the gamma I squares, and this one here is compared, okay, to the sum of the squares of the size of the changes there, yeah? This one here is essentially, this is when the sigma I square comes in, and what you are looking at is some kind of a normalized variance terms there, yeah? So essentially, for example, okay, if sigma I would be the same, then this one would be cancelled by that one. If the delta i's would be the same, then in this case, this term will cancel out, okay, the delta squares there, except an n there, and in this case, you would be looking at the average of the sigma I squares, yeah? So this is some kind of a variance term there. Okay, this one it is just a very simple functions there. It comes out in the limit distributions like in the standard case there. So, next theorem, we assume that S is 0 there. So this means that essentially very, very little interactions there. And now the size of the change, the sum of the squares of the change is going to 0 there, yeah? Okay, of course, they are not going very, very fast there because there was a previous condition, okay, about that one here. Roughly speaking, okay, this is going to 0 a little bit less than 1 divided by square root of n. Okay. In this case, if you are looking at this normalization here, you are looking at the argmax, okay, of a Wiener process or standard Brownian motion minus this function here. This is a well-defined random variable. Why? Because essentially on the tails, this is going linearly away, but we know that, okay, that the Brownian motion is going to infinity at the order of square root of u essentially. So this means that it will be reached, okay, at a well-defined random variable. The distribution of this argmax here is well known, even, okay, the density and the distribution function was computed in the 1960s, okay, so it's a well-defined and well-known factor there, okay. Okay, so third theorem, so there will be tons of them. Okay, now, what we are looking at in this case is the following. The sum of the squares of the size of the change is going to a 0 there. Yeah, it's not going to a number there which is different from 0. In the previous result, it was a 0 there. If you are looking at this process here, this is not a Brownian motion, but essentially some kind of a Gaussian process there, but only defined on integers there. And the covariance structure of this one is given, okay, in a way like that one, but again, the size of the change is incorporated, okay, into the definition there. So those of you who have essentially ever looked at the changes, how to estimate the time of the change, when the size of the change is constant, then in this case, in case of one single panel, the distribution of the time of the change is related essentially to the maximum of partial sums of random variables there, yeah? In this case, the interesting, and this is the new part in this case, that due to the summation with respect to the panels there, okay, these are not the partial sum of the error terms there, but you are looking at, okay, so very, very nicely, Gaussian random variables here. So essentially, this is again an argmax here, but instead of having a continuous process there, now you have some kind of a nice, okay, Gaussian process there defined only on the integers there. So this is the difference. There is nothing like this one in case of one panel there. Again, the question is, okay, so it's impossible to know, of course, okay, so when you have observations there, that's what you are computing, okay, this is essentially a positive number, or it is going to 0 there. By, in a paper, essentially showed that this one here can be extremely well, can be approximated extremely well using the continuous counterpart which was in the previous theorem there. Okay, so for theorem, okay, look at this one here. What is happening? The size of the change is small, but in this case, essentially what we have that, okay, that when you are looking at the interaction between the panels is large. And in this case, essentially, when you are looking at the rate of convergence, it starts slowing down there, yeah? So essentially, there was only sigma squared before. Now you have an additional term there, which is coming from the ratio, which is the sum of the squares of the common factors divided by the sum of the squares of the changes there. The next one here again, in this case, if the size of the change is going to a constant there, then again you are looking at something, okay, which is not continuous anymore. And if you look at this one here, this is the new t there, it is coming from the common factor. In the common factor, there is no summation with respect to n there. So therefore, this is not normal anymore, what you are getting here in the limit, but you have this random work on the sums of dependent random variables there. So this is essentially an additional term is added to that one. Okay, so this is the fifth one here. In this case, okay, so the 0 shouldn't be there. So in this case, when we have that s is infinity, so in this case, the common factor is dominating there. And in this case, you have a rate of convergence like this one. The limit result, it was typically like before, but in this case, when you are looking at this ratio there, this is much smaller than before. Yeah? So you can still estimate the time of the change there, but in this case, okay, the confidence interval, what you are trying to construct, it will be much wider there. The penalty what you are paying is due to the very strong correlation between the panels there, that roughly speaking for the only information what you are getting is based on the common factors there. Oops. And again, you can have the same thing. Again, if the size of the change is constant, then in this case, okay, so it is written in a form like that one. And again, you will get some kind of a discrete limit there. Okay, if you go and look at all the conditions there, because they are, okay, theorems going from 1 to 5 there, so this means that, okay, this covers all the possible cases, as it turns out there. The interesting thing is when you are doing this one, there are essentially 4 different type of limit distribution there. The most interesting one is the continuous when you are looking at the maximum of the Brownian motion minus the drift process there. All the other ones is essentially some kind of a nice, from a mathematical point of view, very interesting and very, very hard cases there. But I would say, okay, so when you are doing any kind of real work there, nobody would use those. Okay, so these are limits when the limits are constants and these type of things, and those very, very difficult to see. Okay, so if you have 0.3, what you computed is hard to know that this is converging to 0.3 or this is converging to 0 there when you have more. So we always use essentially the limit one. Okay, if you would like to do it as a very, very general result there, okay, so you can prove the following. This one here is the sum of the squares of the sizes of the changes there. Yeah? Okay, and if this is normalized by these factors there, so this one is essentially this the sigma I squared delta I squared. This one here is the sum of the squares of the loading factors there, and in this case, okay, this ratio here is converging in distribution there, yeah? And only thing what we were looking at, like down here, okay, which one is the dominating term, yeah? Converges in distribution, it doesn't mean it's converging to the same things there. Essentially, you have 4 or 5 different type of limit distributions there, depending on, okay, how these terms are, okay, so work together, which one is the larger, which is the smaller one. Now, how this is working out there, okay, so these are simulation studies there. So what we have in this case is essentially, this is the histogram of the estimator there. Yeah, so these are essentially the point there. The other one, this red line, what I cannot see, hopefully you can see it, this is the density of the limiting random variable there. Okay, so here is essentially, it stops here at this point there. This is not like it has a singularity, it doesn't have a singularity there. Yeah, and you can see that essentially the fit is very, very reasonable, and you can see that essentially when you are looking at 0 there, this means that essentially the estimator is exactly the point when the change happens there. So I would say, okay, even the convergence to the limit is relatively good there. We got tables today, so it turns out, okay, that these things are working relatively well when the panels, let's say, are 50, and in this case, okay, the number of the observations, the panels are running between 25 and 200 there. Okay. So this is the distribution function, okay, and again, so what we have, okay, these are the simulated one, okay, the blue one is the theoretical one. So again, I would say the fit is a very, very good one. In this case, not the n is 100 is the important one, but the important one is, okay, the t is 1000. Yeah, okay, this is very, very large there. Surprisingly, if you go down, okay, with 1 0 there, then you will get something, okay, which is essentially very, very similar to that one, at least on the upper tails. Okay, so the application part, what we have, and these are the exchange rate there. So what we are looking at is essentially the exchange rate for those currencies with respect to the US dollar there. And this is done in a period there, and I do not remember which one. Okay, in the new pictures we have essentially the days there. So the question is, okay, so whether there is a change, okay, in the exchange rate there. So we run the testing there, of course, the null hypothesis that essentially those are stable. It is rejected, okay, so as my wife would point out, even she could see it. Doing any kind of analysis, so the obvious comes out, okay, that there is a change there, and this is essentially when you have the time of change. Yeah, okay. Okay, so this one here is another countries there, and essentially, okay, the same thing is happening there. Okay, so when you put together, okay, so essentially you have the same thing, and it's visible it's happening there. Yeah. Okay. Oops. Yeah. So essentially, let's see. Okay, these slides are not there. So what you can see in this picture, okay, this is interesting. The following: if you are looking at this exchange rate here, yeah. So you can see that essentially, like, okay, so which one? The best is, okay, the English pound. Yeah, okay, and then you are looking at the other one is the Singapore dollar there. So here is like, okay, 1.45, and here you are looking 1.8 there. Yeah, if you are going to the other slide there, the interesting thing is, okay, so you are start with 8.3, and in this case going up, okay, with 10 there. So you can ask, okay, and this was the questions there, can it happen or not that there is one currency, okay, which is, I would say, it's very bad compared to the US dollar there, and there are essentially very, very big changes in that one. So imagine, okay, that like for $1 US, you will get, okay, 100 bolivar. Yeah, if there is a 10%, okay, so decrease in the value of that one, it will give you 10. Yeah, but essentially same thing is happening to the British pound, like 10% change there. It will become like 145, okay, 15 there. So there is a very, very small change, but the bolivar, okay, is sitting down, okay, and it can happen that this will determine the sum of the squares. The whole thing what I presented here, okay, this was essentially repeated when you are looking at the normalized exchange rate there. So what we did, essentially, what was essentially the exchange rate on the first day when the study started there, it was divided by this rate with the same number there. So roughly speaking, okay, we were looking at relative changes there. And interestingly, nothing changed. So nothing changed there. The analysis became exactly the same there.
But is this
Yeah.
an abrupt change or is it a smooth change?
In this case, okay, so it's an interesting one there. So the test what we had is essentially, and also this procedure there, so we are assuming that essentially, okay, so there is an abrupt change there. If you are looking at the smooth change there, okay, because in this case it is going down there, yeah, then in this case essentially everything will go through there. But it turned out that if you go is essentially further with the analysis there, and you're looking at how it looks like, this is not the only change, yeah? So essentially if you start using the binary segmentation procedure there, then in this case you will find further changes there. So in this case, if you look at it, okay, you can see, okay, that essentially what is happening there. So if you do the segmentation procedure, then you will have the following interesting things there. Then when you are looking at a homogeneous interval, the length of this interval is 30 days, 60 days, or 90 days there, yeah? And it turns out it makes sense because the US Federal Reserve has monthly meetings. And this is when they essentially decide what they do with the interest rate there, whether they leave it, whether they change it, okay, what will happening there. Of course, you cannot assume that, okay, so like if they change it, then they will be like an immediate rush, okay, and everybody will change the exchange rate there, because typically it is expected, so they already prepared that this will happen there. Okay, so one of the changes essentially, as I just saw it, I figure out what is the day there. So in this case, if you are looking at, okay, this big drop here, this is when the US essentially reduced the prime rate, and this was expected that it will not do it. Okay, so essentially there's some things what they were not supposed to do it, but nevertheless, okay, so when you are going for this interval there, the 90 and so on, then in this case essentially you can get very, very good confidence intervals, and I checked it for, it turns out, okay, that the day when the Federal Reserve met, it was really in the middle one, yeah? But they meet monthly, but it doesn't matter, doesn't mean that in this case essentially people start panicking and they are trying to do it. In a few cases, and even it's interesting, okay, so like why the change is not happening instantaneously, in certain countries, okay, their own equivalent of the Federal Reserve will meet 1 or 2 days later, okay, after the Fed in the US met there, so they will react, I would say, okay, 1 or 2 days later there, but sometimes the market reacts, and in a few cases what we looked at it, because I was very surprised that why, okay, so even when the Federal Reserve met was inside of the confidence interval there, why was I was on the very, very right side? Because people expecting some kind of a change there, so the change occurred even before the Federal Reserve met there, and in a few cases it turned out, okay, that the preparation for the meeting was incorrect. Yeah. Okay, so this was my talk, and sorry about, okay, the finance part there, but my talk will be given at Birmingham at the finance department, so this is the reason why I wanted to show those pictures. So
I think the Gini index also, it's not an abrupt change, is it? Is it more a gradual change?
the Gini index, okay, so according, okay, so this UNESCO website there, they think that those are abrupt changes there. Yeah, yeah.
I would say so. When I said this is for me, that is what I pointed out to Lajos, that you see this, there are these gradual changes.
Yeah, that's what I mean.
Yeah.
But you see, as soon as you construct the procedure for abrupt change, that you detect also this gradual change, but usually, yeah, the estimator or balance changes, it needn't be exact. Okay, so that is so if you look at it, it should be somehow, for the model that we are connected, should be somehow always partly.
Yeah, but that's what I'm asking. Do you need a smooth transition model?
So if you do about testing there, okay, these things which based on the cumulative sum, they have relatively very, very good power there when you have essentially this gradient change there, okay? This is not as good. What you will have is essentially when there is an abrupt change there, but essentially again, the null hypothesis of no change will be rejected there, yeah? Okay, the issue is, okay, when you are trying to essentially construct confidence intervals and so on, the issue is, okay, so you are doing this one with respect to t there, and when you have essentially 30 observations and so on, probably what you are looking at, like even there is a gradual change, then to find, okay, the middle one. So yeah.
So finding the change point is not sort of finding the smooth transition, because then once you find the change point, that's probably the middle of the
Yeah,
smooth
yeah,
transition.
yeah,
And
yeah,
then you
yeah.
put a smooth transition model.
If you want to, yeah,
Okay,
yeah,
that's
yeah,
what I
yeah.
mean.
But if you look at,
use
yeah,
smooth transition model.
yeah. But look at, yeah, 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 yeah,
The cat location of the smooth
Yeah,
transition.
yeah, yeah.
and then you can start modeling where
Yeah,
the transition.
yeah. So if you look at this one here, okay, so this is the gene index, okay, when there were changes there. So you can see here, okay, that essentially until this point there, it is a relatively stable one, yeah? If you are looking at this one here, okay, this is a relatively stable one, and essentially it is going essentially in 2 years.
Yeah.
So the question is, okay, so 2 years you can change is an abrupt, okay, or you think that is a gradual change there. Okay, so those people essentially who went through that one, they would say that this was a very, very abrupt change. Yeah. So don't forget, Hungary that time went through essentially an inflation there in those years there when the annual inflation was 120%. Yeah? And this was essentially when if you were paying like your mortgage, okay, due to the high inflation rate there, they multiply what you have to pay monthly with 100. Yeah? So I would say, okay, those were extremely drastic steps there. So very few people would say that those were going smoothly. And again, if something is done in a 2-year period there, let's see, okay, in 25 years, okay, this is a question, you think that this is jumped up, or you think that, okay, so it went relatively smoothly there. Yeah?
It's fine.
No, I'm not saying, okay, just, yeah, yeah. But this is the typical thing, okay, that's whether, okay, this is going smoothly or not there, whether you put a smooth functions or not. Putting a smooth function there, okay, you need, I would say, a little bit more points, okay, to do things like that one. Or you can use, okay, the calculus argument there, if even it is smooth, okay, this is essentially locally, everything is a constant, okay, so. Yeah, yeah, thank you, yeah.
Should we thank lunch?
Oh, thank you very much for coming, yeah.
Do we have any other comments or questions?
So if you can go back to your exchange rate data.
Okay.
So you were saying that obviously with the GDP and things, you had a smaller, 10% was a smaller degree of change. But I think that's naturally taken into account because you've got a smaller variability in the signal as it is.
If you are, so
we know that if you've got the relative change depends on the variability of the signal.
yes, yeah, yeah. So it can be the reason for this one for us. Okay, 3 currencies in Latin America were extremely worrying. One of them was the Bolivar, and there were 2 other currencies there. Then they were jumping up and down. So there was lots of variability, but they were going up there. So in this case, okay, so when my students did the simulation, they showed me, so the question was what to do, whether just kick them out, okay, keep them inside and so on, so with the scaling, and didn't do anything. So probably when you scale it back, then essentially, okay, the variability and this type of things is essentially exactly what you said there, okay? This is what caused that one here, yeah? So there were large variability in the data there, so this means that when you are computing, okay, the size of the change divided by the variability there, it became relatively good looking there, yeah? But we worried, yeah.
And
Yeah.
so you stated at the start that you're assuming that a change is in every panel, but then you would obviously estimate the delta is to be close to 0 if there wasn't.
Yeah.
And in all of the theorems that you were stating, you had things like the delta of the change going to infinity or to 0.
Yeah.
Constant. And how does that relate to the actual number of panels that the change appears in?
Okay.
If the number of panels is say going to infinity, but the number of panels with changes isn't going to infinity.
So okay, so the condition is essentially the sum of the squares of the changes in n panels, how it behaves. Okay, so this means that essentially, of course, okay, like the condition is that this is going to infinity there. You do not need that all of them will change, but large number of them will change and it will be large enough. If you start increasing, okay, the number of the panels there, then in this case, of course, the changes can be smaller. There is a very interesting paper, okay, and in econometrics it is called the Horioki and something else puzzle there. So they were looking essentially, okay, that like some kind of a parity index there. When you are looking at, okay, for every country there, whether there was a change, nothing can be detected there. Roughly speaking, all the tests what they tried was inconclusive. And when they put together the 50 countries there, then there was no change there. It was rejected immediately. Yeah? So don't forget the typical thing is that if you have one single panel, that the size of this change, okay, is essentially large enough in some sense. But when you take the sum of those, okay, and this would be essentially the same amount there, yeah, then in this case the null hypothesis is rejected. So now the issue is, okay, and this was a very, very discussion about econometrica. Now we know that when we looked at 50 countries and they looked at this parity index, it had to be a change, yeah? But they cannot figure out in which countries, yeah? Because there is no change in any of the single countries there. Okay, it can happen that there is no real change. Only thing you rejected the null hypothesis because there is a very, very strong correlation between them, yeah? But this is essentially widely discussed. Okay, inconclusive results for one panel, you put them together, now you have a result there, and in this case you cannot really move further. Yeah.
So there was a discussion in some of the talks last week about identifying from a set of data which subsets.
Yeah.
Have you thought about that at all?
So we didn't really, okay, so thought about that one. Okay, so how to do it? Yeah. So in this case, okay, my thing would be, okay, to look at, okay, the pictures there and try to combine those when essentially you think that there was a change there. To do it automatically, I would say, okay, so yeah, it's nearly hopeless. Yeah, and I would like to point out, okay, so when you do this type of things, of course, you look at the pictures there. So when I showed the pictures, okay, I looked at least a dozen and I picked those who look the best. And I think, okay, this is how real life works. Yeah. Okay, nothing is done as automatically, okay, as we assume. Yes.
From a practical point of view, what do you do if you've got missing observations at some particular time points, or if they're censored? And I was wondering, I didn't really understand the kernel bit, but whether you could change it to somehow where you had irregularly spaced observations.
So in this case, okay, so this is essentially, okay, what I talked about, okay, this was financial data there, and there were no missing observations there, yeah? So we didn't even, okay, so thought about that one. When I mentioned the Gini index and the corruption index there, so essentially we only use the data when there were no missing observations there. And I would say, okay, so this is not really a change point type of things there. Probably I would use some kind of a linear interpolation to replace the missing data there. Yeah. Okay, and also in case of the Gini index, some countries were excluded because according to the website, okay, nobody thought that the data provided by the governments were correct.
High on your corruption index.
Yeah. So I said, okay, bro, they had to put it there. Okay, so into the interesting case about this survey, what the invitation is collecting, it's very, very hard to know how they computed it. Yeah, they are not really willing to reveal it. So what was used, how they got it, and what those are. Yeah, and I assumed, okay, that those will be like integers, but it turned out, okay, those are not really values going from 0 to 10.
Are the computation in the next slide independent of the computation in this one?
This one here, essentially, this is essentially just showing, okay, that how this one looks, okay, on those countries there. When the computation was done, all those curves were used. Yeah, they were put together. Yeah.
It's the same vertical line.
Yeah. Essentially, you will get exactly exactly the same thing. In this case, it was done because the number of these is a lot. So this was essentially done panel-wise, yeah, in each panel there. Then in this case, this line came up there. Okay, 75 cases in the first step. Yeah. In other cases, it came up in the second step when you were doing this binary segmentation method there.
So maybe just to say that to this data set, I asked also to prepare just some kind of diagnostic. So that means that the statistic which is there is depending on the case and how it looked like, and really indicate the change point. There is no, that's really peak around the change.
So here we are looking at, okay, 500 days, and this is I think 1.5 years there. So there is one paper which was published in this electrical engineering journal there, and they are using this exchange rate data there, how to find automatically lots of number of changes there. And the data what they are looking at is not 1.5 years there, but 25 years. Yeah? And in this case, exactly the same pattern will show up there, that you are looking at the 30, 60, 90 intervals there. So roughly speaking, okay, probably the mass model of this exchange rate is essentially putting, okay, this going up and down, okay, lines there, that it is constant, and then another constant, it changes other constant there. The other thing, okay, about the exchange rate that some people believe, because this is certainly non-stationary, no question about that one. What is causing the non-stationarity? That this is like, okay, some kind of a random walk, yeah? Or you have this changing mean there, and again, you have something, okay, which is again non-stationary. So we tried it essentially, we took out, okay, those small changes there, and in this case, it doesn't really look like a random walk there. So maybe this is the cause of the non-stationarity. Yeah. The problem, I would say, with the exchange rate that this is not some kind of a natural process there. So people making the decision about that one.
If there aren't any other comments or questions, let's thank Lajos again.
Thank you very much. Thank you.